So let's do this. The 10 ways in which NASA writes critical safety. Now remember, they're pretty good at being critically safe. Obviously, the Voyager stuff is awesome. All right, most serious software projects use coding guidelines. These guidelines are meant to state what the ground rules are for software to be written, how it should be structured, and which language features should and should not be used. Curiously, there is little consequence on what a good coding standard is. Among the many that have been written, there are remarkably few patterns to discern, except that each new document tends to be longer than the one before it. Okay, that's pretty good. Dark mode, can you dark mode a PDF? I don't know how to dark mode a PDF, dog. Sorry, this is NASA, light mode. Okay. The result is that most existing guidelines can tell well over 100 rules, or the result is that most existing guideline contains well over 100 rules, sometimes with questionable justifications. Some rules, especially those that try to stipulate the use of whitespace in programs, Python mentioned, may have been introduced by personal preference. Others are meant to prevent very specific and unlikely types of errors from earlier coding efforts within the same organization. Not surprisingly, the existing code guidelines tend to have little effect on what developers actually do when they write code. By the way, I'm loving whatever the start of this article is. Whatever NASA has cooked up, the start of this is amazing because it is so right that there is a lot of personal preferences that are written into code guidelines. The most dooming aspect of many of the guidelines is that they rarely allow for comprehensive tool-based compliance checks. Tool-based checks are important since it often infeasible to manually review the hundreds of thousands of lines of code that are written for larger projects. I love everything. I love everything that is currently being stated. Things should rely on automation and tools, and it should have zero personal preference. Okay, things are looking good. Things are looking good. The benefit of existing coding guidelines is therefore often small, even for critical applications. A verifiable set of well-chosen coding rules could, however, make critical software components more thoroughly analyzable for properties that go beyond compliance with the set of rules itself. To be effective, though, the set of rules has to be small and must be clear enough that it can easily be understood and remembered. The rules will have to be specific enough that they can be checked mechanically. To put an easy upper bound on the number of rules for an effective guideline, I will argue that we can get significant benefit by restricting to no more than 10 rules. Such a small set, of course, cannot be all-encompassing, but it can give us a foothold to achieve measurable effects on software reliability and verifiability. Oh, this is sounding so good. I'm liking everything so far. To support strong checking, the rules are somewhat strict. One might say even draconian. The trade-off, though, should be clear. When it really counts, especially in the development of safety-critical code. So I should probably consider this for the bot I'm writing, right? For my Twitch bot / stream recommendation bot. Obviously, I should probably be considering these 10 rules because we need criticality in here, okay? I want verifiability to the max. I want the 10 commandments of programming, all right? Let's see. It may be worth going the extra mile and living within stricter limits than may be desirable. In return, we should be able to demonstrate more convincingly that critical software will work as intended. 10 rules for safety-critical coding. The choice of the language for safety-critical code is in itself a key consideration, but we will not debate it much here. At many organizations, JPL included, critical code is written in C. With its long history, there is extensive tool support for this language, including strong source code analyzers, logical model extractors, metric tools, debuggers, test support tools, and a choice of mature, stable compilers. For this reason, C is also the target of the majority of coding guidelines that have been deployed or developed. For fairly pragmatic reasons, then, our code rules primarily target C, an attempt to optimize our ability to more thoroughly check the reliability of critical applications written in C. All right, you heard it here, people. I know there's a lot of soy devs out there right now, okay? A lot of you guys right now, that when you heard the fact that they used C and they used the word safety critical, you're just like, interns. Again, last time I checked, y'all don't have Voyager out there, okay? You're not GigaChads, okay? You're a bunch of script kiddies LARPing as system engineers, okay? Shut up. Let's see what they have to say, okay? The following rules may provide a benefit, especially if the low number means that developers will actually adhere to them. Each rule is followed with a brief rationale for its inclusion. Rule 1. Restrict all code to very simple control flow constructs. Do not use goto statements, set jump, or long jump constructs. And direct or indirect recursion. I don't know what indirect recursion means. Is indirect recursion just two functions that call back and forth to each other? Okay, so help me understand this one. How would you do something? Because this does happen. This has happened many a times where you have a function that needs to go out and call another function that needs to go do something and do some sort of checking, and then come back through some means that you don't control, especially in languages that, like, if you don't have async await. I guess you just have to block the thread. Is that all it's asking? You just block the thread if you don't have async await, right? And you just sit there and you just block the thread and you just do this in a while loop. I'll have to think of the times that I use, because I technically use indirect recursion when doing reconnecting sockets. And what I mean by that is if I just open up, let's open up, socket, this one. There we go. So I have this reconnecting thing that will literally call a private reconnected that resets the state, then call reconnect, and reconnect will go in here and then call connect. Connect, when it disconnects, will recall connect. So this is technically a form of I guess I could just put this in a while loop and then have an await. I wonder if that's simpler. Now you really got my brain thinking about this. It could just be an endless. I kind of want to think more about that. Okay, I will think more about that. I will think more about that. Prime already broke rule 1. Well, indirect recursion is a very powerful infinite problem-solving mechanism. But I can try it, right? I have absolutely no problem trying something. Right? Rationale. Simple control flow translates into stronger capabilities for verification of often results in improved code clarity. I'd agree. It is a bit snaky to see that on a close, on a close we call reconnect. On a reconnect, we check to see if we're started, and then if we haven't done this, and then if we are connecting, we return. There's a lot of these statements that all exist in ordering that kind of cause this problem to happen. So I can understand this. I can actually argue. I can see why this happens, right? Okay, the banishment of recursion is perhaps the biggest surprise here. Without recursion, though, we are guaranteed to have an acyclic function call graph, which can be exploited by code analyzers and can directly help to prove that all executions that should be bounded are in fact bounded. Note that this rule does not require that all functions have a single point of return, although this is often simplifies control flow. There are enough cases, though, where an early return or an early error return is a simpler solution. That's actually, that's a very pragmatic argument for it. To be completely fair, this is a very pragmatic argument for why you shouldn't do this. And to also be completely fair, my teacher in my junior year or my senior year of college made us do, it was actually my sophomore year in college, made us do an AVL tree. If you're not familiar with AVL trees, it's a type of self-balancing binary search tree that uses rotations. There's four different rotations, right? There's the long right, there's an RR, an LL, or an RL or a LR, and there's these different rotations that occur, and they're actually pretty fun to do. Here, I'll just write it really quickly for you. We'll call this here. I'm just going to write it as A, B, C, right? So if you have a binary tree that looks like this, then you want to reorganize it as B, A, C. And if you have a binary tree that looks like A, B, C, right? You reorganize this as A, B, C. Whoopsies, hold on. A, C, B, and then do this rotation, right? Pretty straightforward, right? It's a pretty straightforward. And he said we had to program an AVL tree. We just had to use no recursion. It was a great learning experience for me. All loops must have a fixed upper bound. It must be trivially possible for a checking tool to prove statically that a present upper bound on the number of iterations of a loop cannot be exceeded. If the loop bound cannot be proven statically, the rule is considered violated. So does that mean you can't use things like array.r.for each? Because there's no technical, the upper bound is dynamic based on the array? Or is it so no while true? Rationale. The absence of recursion and the presence of a loop bounds prevents runaway code. This rule does not, of course, apply to iterations that are meant to be non-terminating in a process scheduler. In those special cases, the reverse rule is applied. It should be statically provable that this iteration cannot terminate. One way to support the rule is to add explicit upper bounds to all loops that have a variable number of iterations. Code that traverses a linked list. When the upper bound is exceeded, an assertion failure is triggered, and the function containing the failure iteration returns an error. See Rule 5 about use of assertions. Okay. Interesting. Rule 3. Do not use dynamic memory allocations after initializations. And there went JavaScript and Go. Damn. Actually, no. To be fair, you could do this without... actually, you could do this in JavaScript and Go. You could do this in JavaScript and Go for the most part. Obviously, anytime you did like Go Func, I'm sure it allocates some amount of memory underneath the hood that you don't know about. All interpreted languages? Not all interpreted languages. That's not fair. Technically, not all interpreted languages. It just means you can't use closures, right? Because closures would be... I assume this means you cannot use closures. Correct? You have to use... you have to do arena... Yeah, you have to do arena allocations effectively. You can't use lists or strings. Yes, you can use lists and strings. It's just that means that whatever memory you allocate is done in the beginning. Meaning, and I think it's talking about the heap, not the stack, is my assumption. But on top of that, my assumption is that, like, let's say you have something that produces a certain set of responses from a server. You have an area of memory that's dedicated to the amount of responses that you could possibly ever need. And then you just simply cycle through it like a ring buffer. So that way there's no allocations happening. So all possible data has already been pre-allocated. Okay, so at the start you should have all the memory you need. Correct. Which means you can totally have strings. It's just that you have to have a predefined area of how much kings you should have. Jesus, that is so much thinking. It is a lot of thinking. It is very interesting. Circular buffers, yeah. This rule is common for safety-critical software and appears in most coding guidelines. The reason is simple. Memory allocators such as malloc and garbage collectors often have unpredictable behaviors that can significantly impact performance. A notable class of coding errors also stems from mishandling of memory allocations and free routines, forgetting to free memory or continuing to use memory after it was freed, attempting to allocate more memory than physically available, overstepping boundaries on allocated memory, etc. Forcing all applications to live within a fixed pre-allocated area of memory can eliminate many of these problems and make it easier to verify memory use. Note that the only way to dynamically claim memory in the absence of memory allocation from the heap is to use stack memory. In the absence of recursion, Rule 1, an upper bound on the use of stack memory can derived statically, thus making it possible to prove that an application will always live within its pre-allocated memory means. I mean, it seems super cool. That sounds nutty. It doesn't actually sound that nutty. This actually makes perfect sense. And I've heard there's a thing that they do in game programming. Correct me if Dan Vale's still here. Correct me if I'm wrong on this one, where they actually do effectively budgets per sub-team. And you have only so much allowance either in memory or in CPU time that you're allowed to spend in your part of the program. And that way, as you exceed it, you can kind of have general reporting being like, hey, physics team, you're using too much time. So therefore, can we do something else? Yeah, that sounds nice. Yeah, and so it's kind of like I know that's a thing. Yeah, I've heard a lot about that. Less for physics for yeah. I know. I gave an example that I understood and that the layman game programmer would understand. Right? 2 little FPS, no bonus this year. Yeah, that's basically true. Broadly speaking, it's a bit more nuanced than Twitch chat allows. But yeah, I'm trying to give my best layman's defense of it. Layman game programmer. I am a layman game programmer. I have programmed small games, but I understand that I am no game programmer. All right, Rule 4. No function should be longer than what can be printed on a single sheet of paper in a standard reference format with 1 line per statement and 1 line per declaration. Typically, this means no more than about 60 lines of code per function. Okay, that's pretty fair. That's pretty fair. Like 60 lines is a good amount of room for you to be able to figure things out. Well, Uncle Bob only allows somewhere between like 3 to 5 per function. 60 lines of code is like a lot. Well, it said on a single sheet. On a single sheet. Right? This is just printed on a single sheet, which means about this. Notice that it's not like strictly a hard rule, but it's a hard rule in the sense that what can be printed on paper. I feel like you can express quite a bit in 60 lines of code. There has to be some way in which you can break this rule, but I feel like I feel like I could generally and easily write code with 60-line maximum functions. Like, I don't feel like that would be hard at all. Yeah, Go standard library has thousands of lines. Yeah, but Go standard library is, I wouldn't necessarily look at Go standard library as one of the cleanest, nicest piece of code ever written. Okay, I personally think the Go standard library is pretty much, I would call it a hot garbo when it comes to reading it. Rationale. Each function should be a logical unit of code that is understandable and verifiable as a unit. It is much harder to understand a logical unit that spans multiple screens on a computer display or multiple pages when printed. Excessively long functions are a sign of poorly constructed code. I mean, I generally agree with this statement. I think it's pretty rare to find code that's actually longer than 60 lines of code. I think generally when you do, A, it's like something that's very explicitly difficult and needs to all be together due to locality of behavior, or B, it's a horseshit function, right? Unless if you write React. I believe what I said stands. All right, rule 5. The assertion density of the code should average to a minimum of 2 assertions per function. Assertions are used to check for anomalous conditions that should never happen in real-life executions. Assertions must always be side effect free and should be defined as Boolean tests. When an assertion fails, an explicit recovery action must be taken, e.g., by returning an error condition to the caller of the function that executes the failing assertion. Any assertion for which a static checking tool can prove that it can never fail and never hold violates this rule, i.e., it is not possible to satisfy the rule by adding unhelpful assertion true statements. I feel like I like this rule a lot. I feel like there's something that's very good about this rule, and I feel like I need to exercise this more. I feel like I still need to keep on doing this because, like I said, I still do quite a few assertions in my code base, right? I do this quite a bit, but my current assertions right here actually hard crash my program. So when I have somehow internally created a message that does not conform to the expectations that I'm getting, then I believe that I have goofed up so hard that it needs to blow up. The result pattern everywhere then? Effectively, it's the result pattern everywhere. Rationale. Statistics for industrial coding effort indicate that unit tests often find at least one defect per 10 to 100 lines of code written. The odds of intercepting defects increase with assertion density. Use of assertions is often also recommended as part of strong defensive coding strategy. One thing that's really nice is that if you can come up with any sort of fuzzing strategy, you can actually test your program, right? You can actually completely test your program to the sense where you can just throw at it a whole bunch of random stuff, and somewhere within your program, you should be having actual defensive statements being made to ensure that further down asserts are never actually happening, right? And so you can actually also drop a lot of specific unit tests for fuzz testing using this, which is pretty crazy. Assertions can be used to verify pre- and post-conditions of functions, parameter values, return values of functions, and loop invariants. Because assertions are side effect free, they can selectively disabled after testing in performance-critical code. Let's see, a typical use of assertions would be the following. If C assert P is greater than equals true, return error. With the assertion defined as above, define C assert. Debugging, failed, assertion, file line, all this stuff, false. Okay, so there's some sort of test debugging. Let's see. In this definition, file and line are predefined by macro preprocessors to produce the file name and line number of the failing assertion. The syntax #E turns the assertion... Hold on. The syntax E turns the assertion condition E into a string that is printed as part of the error message. In code destined for embedded process, there is, of course, no place to print the error message itself. In that case, the call to test debugging is turned into a no-op, and the assertion turns into a pure Boolean test, and that enables error recovery from anomalous behavior. What's it called? So this is kind of where I started on my little journey of this power of 10 thing, is that I had Yoran join us from Tiger Beetle, and they do this. He was very specific about this thing, and he can just throw anything at Tiger Beetle, any data, anything, and it will behave properly at all times. It does something like 200 years worth of query testing every single day on every single build. And so it's just constantly getting hammered, and it has asserts everywhere. It's a super cool project. Data objects must be declared at the smallest possible level of scope. This is just C not having proper error handling and syntax features. I strongly disagree with that statement. Asserts are in fact very, very useful. And Tiger Beetle is written in Zig, which has proper error handling utilities. It has result objects, but it has its own error handling result objects, which actually provide much better stack traces than standard errors. It's very, very cool. I think he said 8,000 asserts existed at the time of the interview. Yeah. Asserts are not error handling. Asserts are, in fact, not error handling. They are invariant hard stops, if you will. Let's see. Is it any different than just returning an error in Zig? You return an error in Zig. You return an error in Zig or a value in Zig. But it's an error value. Yeah, they don't hard stop here. They have to have recovery, which I think is fine. Which I think having a hard stop here or having a soft stop in some sort of error recovery mechanism, but you build error recovery mechanism in everything. This rule supports basic principle of data hiding. Clearly, if an object is not in scope, its value cannot be referenced or corrupted. Similarly, if an erroneous value of an object has to be diagnosed, the fewer number of statements where the value could be assigned, the easier to diagnose the problem. The rule discourages the reuse of variables for multiple incompatible purposes, which can complicate fault diagnosis. OP potentially mentioned? Is that what I'm hearing? I'm not concretely understanding Rule 6 other than it just sounds like what I think it literally, I mean, it just sounds like you just define it where you use it, and that's always the smallest one. Is that what it's saying? It sounds, yeah, are we encapsulating here? All right, rule 7. The return value of non-void functions must be checked by each calling function, and the validity of the parameters must be checked inside each function. Hold on, I don't know what that means. Hold on, what does this mean? This is possibly the most frequently violated rule, and therefore somewhat more suspect as a general rule. In its strictest form, the rule means that even the return value of a printf statement and file close statements must be checked. One can make a case, though, that if the response to an error would rightfully be no different than a response to a success, there is little point in explicitly checking the return value. This is often the case with calls to printf and close. So actually, that's one reason why I really do like. I think I have some Zig in here. Let's see. So this right here. So dinit can return an object to see if anything happened to it while it was going on. And I am explicitly stating, in a very explicit sense, that I do not care about the return value. Right? There you go. Do you see that? So when I do this... Oh, whoopsies. Was that just... hold on. Let's see if I can just do this. Foo... I can just do that. Let's see, if I just call foo, I'm pretty sure if I just do foo, I thought, if I'm not mistaken, that should, it probably isn't working with the ZLS LSP. I haven't set it up correctly. Apparently there's a way to do build on this, Zig build. Can I do that? There you go. Nice, right there. So this is supposed to show up in my editor. It's supposed to show up right here, but this is just saying the error union is ignored, meaning that I am not handling this, I'm simply ignoring it, or I'm simply just not using it. And so I can do this saying, I know there's something that happens. I just don't care that it happens, which I think is pretty great. I think that's a great thing to do. I actually really do enjoy this about Zig. And I think Rust has the same thing, except for they just do it as warnings when you disregard the a result that's returned or an async that's returned. I like that rule, though. I think that's a great rule. I think that's a great rule. In cases like this, it can be acceptable to explicitly cast the function return value to void, thereby indicating that the programmer explicitly and not accidentally decides to ignore the return value. Yeah, so that would be the underscore, explicitly casting it to a void. In more dubious cases, a comment should be present to explain why the return value is irrelevant. In most cases, though, the return value of a function should not be ignored, especially if error return values must be propagated up the function call chain. Standard library famously violates this rule with potentially grave consequences. See, for instance, what happens when you accidentally execute strlane 0 or strcat this with the standard C string library. It's not pretty. By keeping the general rule, we can make sure that exceptions must be justified, with mechanical checkers flagging violations. Often, it will be easier to comply with the rule than to explain why non-compliance might be acceptable. I like that. This is great. This is just generally a good rule. You know, so much of programming is just learning some of these techniques to not shoot yourself in the foot. The use of preprocessor must be limited to the inclusion of header files and simple macro definitions. Token pasting, variable argument lists, ellipses, and recursive macro calls are not allowed. All macros must expand into complete static units. The use of conditional compilation directives is often also dubious, but cannot always be avoided. This means that there should rarely be justification for more than one or two conditional compilation directives, even in large software development efforts, beyond the standard boilerplate that avoids multiple inclusions of the same header file. Each such use should be flagged by the tool by a tool-based checker and justified in the code. I mean, definitely not wrong on being careful about the pre-processing macros. I have never had more problems understanding code than pre-processing macros. Pre-processing macros are one of the hardest things ever. This rule would actually complicate our game so much more. I don't like this at all. Interesting. I don't like preprocessors in general. Yeah, I can understand that. Preprocessors can definitely cause a whole bunch of problems. And people more generally call them macros. Generally, macros can be very nice, but they also generally can be massively difficult to understand. Like very, very difficult to understand. Thank God C# does not have macros. Yeah, they are an incredible hammer. They're an incredible tool, but just like all incredible tools, they are just super dangerous. The C preprocessor is a powerful obfuscation tool that can destroy code clarity and befuddle many text-based checkers. The effect of constructs in unrestricted preprocessor code can be extremely hard to decipher, even with formal language definitions in hand. In a new implementation of C preprocessors, developers often have to resort to using earlier implementations as a referee for interpreting complex defining language in the C standard. The rationale for the caution against conditional compilation is equally important. Note that with just 10 conditional compilation directives, there could be up to 2 to the 10 possible versions of the code, each of which would have to be tested, causing a huge increase in the required test effort. I mean, this is fantastic points here, right? It is a good point that especially conditionally compiling is just a nightmare. Generally speaking, conditioning compiling is a nightmare, though there are times you just have to have it. I mean, I think that's what I like about this is that this is a very pragmatic rule, recognizing that you cannot avoid conditionally compiling, but conditional compile is also very, very difficult and is also very awful, right? It's yes, the Rust cargo feature. I assume the Rust cargo features purely exist mostly due to the fact that Rust compilation is slow, and most people that I know have not been too into Rust binaries. And it's more just the worry of the slow-ass compilation time. Now, I'm sure Rust binaries at the end would be very, very important, but as far as I can tell, a lot of it has to do with just the slowness. It's more of a need out of slowness, which actually adds a whole bunch of... I always end up getting something like clap, and then I forget feature derive, and then I have to get feature derive, or then I get request, and then forget request feature whatever, or you get any of this, and it just gets worse and worse and worse. Have you seen AutoSAR C code? I'm sure it's terrible. Clap, sorry. Yeah, you got to get clap, dog. All right. The use of pointers should be restricted. Specifically, no more than one level of dereferencing is allowed. Pointer dereference operations may not be hidden in macro definitions or inside typedef declarations. Function pointers are not permitted. Pointers are easily misused, even by experienced programmers. They can make it hard to follow or analyze the flow of data in a program, especially by tool-based static analyzers. Function pointers, similarly, can seriously restrict the types of checks that can be performed by static analyzers, and should only be used if there is a strong justification for their use. And ideally, alternate means are provided to assist tool-based checkers to determine flow of control and function call hierarchies. For instance, if function pointers are used, it can become impossible for a tool to prove absence of recursion. So alternative guarantees would have to be provided to make up for this loss in analytical capabilities. How do you do like async stuff? Interrupt routines? Yeah, let's see. I don't think they do async. I'm sure they do async. That's the neat part. You don't know. You have to do some sort of mutex usage, right? Some sort of semaphore mutex lock usage, and then some other reference to the memory, right? Async is not deterministic, so nope. Well, it's not that it's not deterministic, but you have to do some level of it, right? Like imagine you have a probe. Here's my probe, and bro has a little camera on it, right? And it's taking a photo. Well, at some point, you take the photo. It goes through, it processes it, dumps this all on memory, and when it's done, it says it's done, and then something has to wake up. So like even interrupts waking up certain parts of the code has to be, isn't that also some level of a function pointer? Yeah, mutex. I would just assume it's a mutex lock, right? So my assumption would be that you have a piece of code that has some sort of, on photo, right? and you are sitting here going like this, you're doing acquire or whatever the semaphore of 1 is. Whatever the semaphore of 1 is in C, I forget what it is, lock, unlock, or lock, acquire, whatever it is, and it just sits here and waits. And then when a photo comes through, then it goes through here and processes all the code and then goes back up here and goes back onto this thing. I like this. Okay, so this one seems harder. All code must be compiled from the first day of development, with all compiler warnings enabled at the compiler's most pedantic setting. All code must be compiled with these settings without any warnings. All code must be checked daily with at least one, but preferably more than one, state-of-the-art static source code analyzer, and should pass the analysis with 0 warnings. I mean, that seems pretty reasonable, honestly, especially if you're starting out brand new. Like, if you're starting out brand new, you should be able to do this one. There are several very effective static source code analyzers on the market today, and quite a few freeware tools as well, too. There you go. There is simply no excuse for any software development effort not to make use of this readily available technology. It should be considered routine practice even for non-critical code development. The rule of 0 warnings applies even in cases where the compiler or static analyzer gives an erroneous warning. If the compiler or static analyzer gets confused, the code causing the confusion should be rewritten so that it becomes more trivially valid. Many developers have been caught in assumptions that a warning was surely invalid, only to realize much later that the message was in fact valid for a less obvious reason. Static analyzers have somewhat of a bad reputation due to early predecessors, such as lint, that produced mostly invalid messages. But this is no longer the case. The best static analyzers today are fast, and they produce selective and accurate messages. Their use should not be negotiable at any serious software project. To be fair, I'm not a serious software guy, so that makes sense. Based and amazing. Based and amazing. Best rule 10. I think this makes, I honestly think this one just makes complete practical sense. It's very difficult to probably apply this to a lot of projects, though. Like, what could you do with JavaScript? We can all agree that lint sucks in JavaScript. Most of ESLint is complete garbo. It's mostly complete garbo, ESLint. It's mostly just people's opinions about what is good and what is bad. No, you can't. Res and reject are in fact, or res and reg are in fact bad arguments to promises. Right? What is it? Don't I have some JavaScript in here? Right? When people are like new promise, what's it called? Res, reg. Actually, excuse me. Right? Just delete ESLint. Yeah, I agree. The first 2 rules guarantee the creation of clear and transparent control flow structures that is easy to build, test, and analyze. The absence of dynamic memory allocation stipulated by the 3rd rule eliminates the class of problems related to allocation and freeing of memory. And let's see, the use of stray pointers, etc. The next few rules, 4 to 7, are fairly broadly accepted as standards for good coding style. Some benefits of other coding styles have been advanced for safety critical systems. E.g. the discipline of design by contract, can partly be found in rules 5 to 7. These 10 rules are being used experimentally at JPL in the writing of mission-critical software with encouraging results. After overcoming a healthy initial reluctance to live within such strict confines, developers often find that compliance with the rules does tend to benefit code clarity, analyzability, and code safety. The rules lessen the burden on the developer and tester to establish key properties of the code, e.g. termination, or boundness, safe use of memory and stack, etc., by other means. If this rule seems draconian at first, bear in mind that they are meant to make it possible to check code where very literally your life may depend on its correctness. Code that is used to control the airplane that you fly on, the nuclear power plant a few miles from where you live, or the spacecraft that carries astronauts into orbit. The rules act like seatbelts in your car. Initially, they are perhaps a little uncomfortable, but after a while, their use becomes second nature, and not using them becomes unimaginable. I love this document. Even if I don't agree with all the rules, I love this document. I am just shocked that anything produced by the government could be as coherent as this is. This is exceptionally coherent document that seems to have been written by somebody who is just trying to be practical, and that's that. Love it. The name is the Primeagen.